Hey kids, welcome to the last topic of Unit 8. The book problems are good, but I do want you to stick around to the last problem of this video because I'm going to show you how AP likes to test this topic. But before that, normally we save warm-ups for live sessions, but since we don't have a live session for either our A or B days, Tuesday or Wednesday, I'm going to go ahead and do the warm-up in the video. The base of a solid, those words mean Play-Doh to you. The base of a solid, finding the volume by using the base and building up from the base. That's Play-Doh. That's not revolution. That is not discs. That is not washers. That is not shells. All of those volumes are created by spinning an area. Volume from a base is building up, right? Those problems that we practiced in the previous video, the Play-Doh problems. The reason I wanted to do this warm-up with you is because every Play-Doh problem that we have done has had the cross-sectional slice perpendicular to the x-axis. So every integral was integrating dx. This time, I've told you that you are making slices perpendicular to the y-axis. So what does that mean for you? You're going to be integrating dy. Now, what shapes am I going to put in my Play-Doh? So remember, you're thinking about taking this shape, this 2D XY plane, laying it down on the ground, and filling the base with Play-Doh. Fill the base with Play-Doh. Before now, we had squares, we had semicircles, we had triangles, we had rectangles, and you laid the shape in the Play-Doh, and then you would pick the shape up, and the line, the side of the square, the diameter of the semicircle, right, the side of the rectangle was perpendicular to the x-axis. So you integrated dx. Now, I'm going to have you lay shapes in here, but the shape is going to be perpendicular to the y-axis. What is the shape, by the way? An isosceles right triangle. So right away, my brain just went to, well, an isosceles right triangle is 45, 45, 90 triangle, where the height and the base are the same. And the longest leg is called the hypotenuse, right? Isosceles means the height and the base are the same. Why do I care about that? Because you know that what we're going to do is put those shapes in our Play-Doh. It's an isosceles right triangle, but the hypotenuse is on the base. Think in the Play-Doh. So every hypotenuse, each one of these triangles is pointing at the y-axis, and the hypotenuse is in the Play-Doh. So what was our strategy? We put the shapes in the Play-Doh, then we took one of the shapes out, picked that out, and we wanted to figure out the area of this triangle. Now remember, it is an isosceles right triangle, but its area is 1/2 base times height. Remember, though, since an isosceles, the base and height are the same. Do you remember how to go from the hypotenuse? And why do I care about the hypotenuse? The hypotenuse lays in my Play-Doh. The length of every hypotenuse goes from the y-axis out to that diagonal line. That diagonal line. So that's why the hypotenuse I care about getting in my area formula, because I am just going to sum all the areas of my shape. That is my Play-Doh strategy. Play-Doh strategy, remember from the last video, is sum the area of the shape you laid in Play-Doh. That's not how you spell laid. Right? And then you're going to multiply dx or dy depending upon where your slice points. So maybe you remember, maybe you don't, but hopefully you can dust that off. It's been a long time since you've been in geometry. If you have a 45, 45, 90 triangle and you know the hypotenuse, you can get the legs by dividing the legs by √2. How does that help? Because the area of a formula is 1/2 the area of a formula. The area of a triangle is 1/2 base times height. But remember, my base and my height are the same because it's isosceles, hypotenuse over √2, hypotenuse over √2. I'm going to sum all of those up. All of those triangles up. I osmosis the 1/2 out. In truth, I'm going to osmosis these denominators out as well. What is √2 times √2? That's also 2. Osmosis that out, so I'm going to get volume equals 1/4. Hypotenuse times hypotenuse is the same thing as the hypotenuse squared. And again, our hypotenuses all point at which axis? Right? That's when I make the decision. Am I integrating dx or dy? The slice is the slice in here, the strip, just like when we were doing revolution, the strip is perpendicular to the y-axis, so you're going to integrate dy, and these numbers need to be y numbers. And your hypotenuses, have to be in terms of y. So what's the length of every single one of those hypotenuses? The length comes from the y-axis to this line. Since I'm integrating dy, I need to get the function in terms of y. The length of every hypotenuse. X is a length. X, there's my x length. Length, each one of those lengths comes from 4 minus 2 times the height. So put your hypotenuse in there. You start, the triangles started in Play-Doh at y equals 0. Where did they stop? The y-intercept of this line. Y-intercept anytime, any place, anywhere is make x 0. The y-intercept is 2. I forgot to write down this answer, but you can just put this into your calculator. Remember, you lie to your calculator, sadly. And you math 9 with 4 minus 2x squared dx, x equals 0, x equals 2, and divide your answer by 4. Okay? Play-Doh. All right, let's move on. Arc length. All your book problems are going to ask you for the length of a curve from here to here. AP might do that as well, but AP also likes to use this in a perimeter question. So that's what I'm going to do at the very end. So if you remember Unit 8, Unit 8 started with area. We went from area to volume. We spent a number of days on volume doing discs, washers, shells, and from a base or Play-Doh problems. And now we're ending up with perimeter. Area is 2-dimensional, volume is 3-dimensional, and perimeter is 1-dimensional. Right? Kind of cool. Don't know why we didn't do perimeter first. Whatever. I just want you to be able to compute the length of a curve, and I want you to apply to a perimeter question. So if we were in person, I would have handed everybody a piece of paper, a ruler, some stickers, and some dental floss. And you would have said, what is dental floss for in calculus class? Well, on your paper, I would have had you hold down one end of the dental floss at 0, 0 with a sticker, and you would have had a little bit hanging off here. Then I would have asked you to pull the dental floss up to this height here and put another sticker on top of your dental floss to kind of nail it down there. And I would have asked you to do that 5 times. And you would have had a little bit more dental floss hanging out here. Whoops, I meant that to be a pen. Then I would have asked you to cut or just ignore those pieces, and I would have had you take the dental floss out from the stickers, pull it straight, and lay it on your ruler and measure it. And I would have said, how long is your dental floss? And I would get answers like, oh, it's between 7 and 8 inches. And then I would have said, oh, gee, I can't remember if I did. I think I did inches. I think I scaled the paper to inches. Or I had some people get pretty good and say, well, I think it's 7.5. Somebody else would be like, no, I think it's a little less than 7.5. Somebody else would say, no, mine's a little bit more than 7.5. But it was all of the answers were around 7.5. It's amazing how close that answer is to the exact length of the curve. So again, we all guessed, the guesses were somewhere around 7.5 inches, I think. Doesn't really matter. If you don't care about the theory, fast forward me, right? Ignore me, play your music, listen to your, put your AirPods in, whatever. But it's kind of cool where this comes from. Estimating the length of a curve using line segments means starting at some point A and stopping at some X value B. Chop up your curve into discrete line segments. You can figure out the length of each one of those segments. It's straight, right? And then add them up. You're not going to get the length of the curve, but you're going to get close. Well, I'm going to look at one interval here between the 5th and the 6th point. Look at what I drew. Going from 0.5 to 0.6, change my X, change my Y, and got a hypotenuse. Yeah, who's there? Come on in. Who's in? Who's coming? Who dis? Pythagoras, come sit down, Pythagoras. Thanks. We missed you. You haven't been around for a while. Love our Pythagoras, don't we? The length of this hypotenuse, which I can make a hypotenuse out of every single one of these line segments. I can do delta x squared plus delta y squared, take the square root, and I get the length of the hypotenuses. Hypotenuses? I don't know. Thanks, Pythagoras. Then I can add those all up. Then what if I make n go to infinity? The number of line segments. I don't increase my space. I go my horizontal space. I'm still going from A to B, but I take the number of line segments to infinity. That makes those line segments infinitely small, but I can still use Pythagoras to find the length of all of them, and I can still add them up. That's the limit. The length of a curve is a limit as the number of line segment goes to infinity, starting with the first line segment, going to infinity, right? Because I can fit an infinite amount of line segments in here. I can't do it. I can't draw it, but I can do that abstractly. And it is just summing a bunch of hypotenuses. Now, hopefully, maybe you can see where I'm going. I'm going towards calculus. Can you see it? I'm not there yet. That's not a Riemann sum. Remember, a Riemann sum is a sum of products. This is not a product. It is a sum, though. I'm about to really geek out on you here. You ready? I want to get to a Riemann sum, which means I need a product. So I'm going to multiply the right-hand side of this equation by 1. Check it out. There's my 1. Do you agree that the square root of 7 over 2 is the same as the square root of 7 over the square root of 4, which is the same as the square root of 7/4? Do you agree with that statement? That's what I'm going to do here. See what I did? I dropped this radical down, and I squared delta x, which means the square root of delta x is still delta x, and this delta x I just left alone. Do you agree that 7 plus 4 over 3 is the same as 7/3 plus 4/3? That's what I'm going to do next. Delta x squared plus delta y squared over delta x squared. I'm just going to give this denominator to both and make two separate fractions. Do you agree that 7 over 3 squared is equal to 7 squared over 3 squared? I'm going to use this property backwards. Do you see what I have here? I'm going to make this delta x over delta x all squared. And I'm going to make this delta y over delta x all squared using this property. But what happens with delta x over delta x? Hello, that's just 1. Now I have the sum of a product. I'm not done yet either. Look at this. I didn't make this into one group yet. Now I did. What is this? Change in y over change in x. What S word goes with change in y over change in x? What S word does that? Slope, my friends. You're in calculus. What D word goes with slope? Derivative, my friends. And since we're going to infinity, this delta y and delta x, the change in y and change in x is getting super, 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 super small. So I'm going to take my Riemann notation, my sum of a product of hypotenuse times delta x. Since I'm going to infinity, I'm going to change this to dy over dx, and I'm going to Leibniz this formula up, which means it is nice and smooth. The arc length is the infinite sum starting at a, which is an x value, and stopping at b, which is an x value, of the hypotenuses. Notice that the arc length formula is an integral with a derivative in it. That says, though, that y prime exists. Y prime has to exist. If you're going to use the derivative dy dx in the formula, your derivative has to exist. So start thinking about, when am I going to have issues with my arc length formula? So this is where then I go back and I say, hey, what was our guess for the arc length of sine x on 0 to 2 pi? Let's check it out with our calculator and our formula. OMG. So notice this was my A and this was my B, start and stop. My function was sine x. My derivative was cosine x. dy dx exists and is continuous everywhere. So in my formula, 1 plus cosine of x all squared. And look at what I got. How close was our guess? Again, I would always have somebody guess 7.6. So somebody would be like, yeah, I won. Of course, it's 7.640, but good enough. All right. So the formula is just the formula, right? But as I said, inside the formula is dy dx. So using that formula depends upon dy dx existing, which means your function's differentiable on your interval, right? Maybe I'm not differentiable, but it's not in the interval, so what do I care? But look at this graph. Can you see the problem? Absolute value of x is not differentiable. And the interval they gave me, I can see it. Can you? Can you see the point of non-differentiability? Dagger absolute value, dagger corner in my graph. So the ways to deal with that, though, I can still find the length of the curve by either A, breaking this up into two pieces and just adding the pieces together, or using the inverse. I prefer not to use the inverse if I don't have to. And I don't, firstly, finding the inverse of absolute value doesn't have an inverse. It's not a real function, right? You have to remember that absolute value is actually a piecewise function. And it's a piecewise function where you can get rid of the absolute value sign and just use x as long as x is positive. You can get rid of the absolute value and use negative x when x is negative. So I took my expression, I dropped absolute value, and I used negative x from -4 to 0. I dropped absolute value and used positive x where my x's were positive. Now notice I didn't include 0. A point has no dimension. So if I add this length to this length, doesn't matter whether, right? A point has no dimension. I'll be fine. So notice though, I couldn't just use y. I had to say y is equal to x squared plus 4x minus x, which means y is equal to x squared plus 3x. Y prime is equal to 2x plus 3, and y prime exists. 2x plus 3 is a continuous function, so the derivative exists. Notice though that that's from -4 to 0. Then I clean this function up. And I put the derivative in. Don't forget to square the derivative. Remember your this really, if it helps you, right? Remember Pythagoras is a sum of squares. So just think of, if it helps you, put a square everywhere, right? Because 1 squared is just 1. I am integrating with respect to x. So my function is in terms of x, and my limits of integration are in terms of x. I know that I have a differentiability issue at 0, but I can still put 0 into both of these derivative rules and nothing happens, right? It doesn't blow up. And what am I going to do with those two answers? And that's what I get. Okay, so there's an example of finding arc length, even though I have a differentiability issue in the middle of my interval. Here's another example, and unfortunately, this is a poorly drawn. This is the cube root of x, which has a vertical tangent at 0. This is -8, and this is 8. So let's say you didn't think about the fact that it has a vertical tangent. So you're like, okay, this is no big deal. I just need y prime. Y prime doesn't look like an issue until you realize y prime is really, and what have you been taught forever and ever and ever? You can't have x in a denominator. Well, you can, but what can't you put in for x? Anything that makes the denominator 0. So y prime does not exist at x equals 0, and x equals 0 is in the middle of my interval. This is a big uh-oh. I can't just split this one up, because if I try to split it up, I'm still going to have to use this derivative rule. So I can't go from -8 to 8, certainly, because y prime is 1 over x to the 2/3. But you know what? Even if I made it -8 to 0, and then 0 to 8, I'm still have an issue with, because remember, your calculator is going to do the fundamental theorem, right? Not really, it's going to estimate it, but it's going to put a 0 in there. It's going to blow up. Can't do that. So if I can't split it up, my other option, right? Derivative is a dagger, is to use the inverse, right? I can't use it. I mean, the arc length is the arc length. Who cares how I integrate it? So I took y equals x to the 1/3 and got x by itself. But it's not -8 to 8 anymore, is it? -8 and 8 are x numbers. So what do I need? This point is -8 comma cube root of -8. This point is 8 comma cube root of 8. -2 to 2. And notice I'm going to find the derivative of x with respect to y. 3y squared has no differentiability issues. So I can put that into my formula. Don't forget to square it. You are doing Pythagoras and going from -2 to 2. Just plug that into my calculator. That's what I got. Don't forget, when you put something into your calculator, it's 3 places past the decimal. All right. So here's my strategy for finding the length of a curve. And again, remember I told you AP likes to apply this in a perimeter problem. Is your function continuous? I don't know how many times I need the arc length if my function is not continuous. But if it is, I'm certainly going to go on and just put it in. If it's not, do I need to split it up? Maybe there's a hole or something like that. Or a jump. Don't see this happen very often. I don't care about the arc length of something that's not continuous. This happens though. Is my function differentiable? And I did 2 examples, one that we split up and one that we had to use the inverse for. If your function is differentiable, find y prime and go on with yourself. If it is not differentiable, you think to yourself, do I need to use the inverse or do I have to split it up? And that decision is based on what your derivative rule is. If your derivative rule is not defined somewhere in the interval, you've got a problem. Then you're going to have to use the inverse. Then you use your formula. And I should have written both formulas. Okay. So as I promised you at the end, I'm going to do an example that AP might give you. Find the perimeter of this region enclosed, and you should recognize that. That's all the Plato problems we did at the beginning started with this shape. Algebra 1, x squared plus 1. Bounded by x equals 0. That's the y-axis. X equals 2. Vertical line, y equals 0, which is the x-axis. They don't want the area. They don't want the volume. They want the perimeter. The perimeter is the sum of all the sides, right? That's what a perimeter is. Add up all the sides. How long is that side? 1. How about the bottom? How long is that? How about the right side? How high is this? Well, when x equals 2, y is equal to 2 squared plus 1. So y is equal to 5. Plus a side that's not straight. How do you get the length of that curve. The length of the curve comes from our arc length formula. I have no differentiabilities there. So the square root of 1 squared, if you want to help remembering the squared, y prime squared dx, starting at 0 and stopping at 2. And y is equal to x squared plus 1. Y prime is 2x and has no issues. So 8 plus whatever this is. Didn't write it down, sorry. That is my perimeter. All right. All right, so again, congratulations for getting through Unit 8. And when we get together on either Thursday or Friday, we will do some wrap-up and some review of the entire unit. You will have the know how you did on your quiz, and we'll start getting ready for the test, but the test won't be until 2 weeks from this past Thursday and Friday, or a week from when we come back, okay, or when I see you next, either Thursday or Friday. The test will be the next week. All right. All right. I will see you then. I hope you enjoyed some of your asynchronous days. See ya.